Recording. Okay. So now, welcome you all to our regular colloquium at SAAO South Africa. So our today's speaker is Dr. Arun Kumar Awasthi. He is associate researcher in the School of Earth and Space Sciences, University of Science and Technology of China in Hefei. And he's a very good friend of mine. He's also part of our, we both are founding member of one organization in India that is called United Science Foundation. And Arun Awasthi is a very knowledgeable person in solar physics that I know. We both attended University of Allahabad for our bachelor's and master's in physics. Then we both moved to Physical Research Laboratory in Ahmedabad, India, for our PhD programs in different fields. He did his PhD in based on X-ray studies of solar eruptions and physics behind that. So I will not waste much of our time for his introduction. He will introduce himself through his work. Let us welcome Arun Awasthi again. Arun Awasthi.
Thank you very much, Neil, for inviting me for this prestigious opportunity of giving a colloquium at SAAO. As Sunil introduced, my name is Arun Kumar Awasthi. And today I'll be talking about probing the pre-eruptive magnetic field structures from the observations we obtain in the evolutionary phase of solar flares. So this is kind of a very complicated title. So I will, as we move on, I will try to phrase by phrase introduce everything. So before moving on, as Sunil introduced, I did my PhD completed in 2014 from Physical Research Laboratory, Ahmedabad, India. And then for my postdoctoral research of 2 years, I moved to Poland. And before my present affiliation as associate researcher in the University of Science and Technology in China. So my collaborators are Professor Rui Liu and Professor Yuming Wang of USTC, and of course, many collaborators from Indian and Polish side are there. So before moving on to the main section of the presentation, I would like to introduce the X-ray intensity. So here I am presenting the X-ray intensity profile of 26 August, just last month. And I would like to show how the disk integrated X-ray emission looks like. So there were a lot of bursts which we can see. So based on the peak emission of burst, we call them as A class to the minimum level of flare and X class to the highest intensity peak. So before many excursion, we can see in the duration of approximately 12 hours of observation, the sun in fact erupted at 18 UT on 26 August. So why eruptions are important? Eruptions are actually the one which forms space weather, and space weather is very important because it directly connects to the Earth system and beyond. We see the auroras, we see magnetic field changes, bow shocks and everything on Earth, Moon, even Saturn and beyond. This is governed by the activities which are occurring on the sun, sometimes constantly in the form of solar wind and sometimes intermittently, which we see here in the form of these small excursions before this large excursion which gave rise to an eruption. So this is just a profile, but unlike astronomy, in solar physics, we have the privilege of observing high resolution observations from space as well as ground. So for this event, I would like to show the movie of the activities which have gone around in this duration, and finally the eruption which we see in the form of this C-class flare. So here I am showing you the movie of 171 angstrom extreme ultraviolet channel observed from Solar Dynamics Observatory operated by NASA. And this particular wavelength channel is very important because here we can see the dark features which are kind of visible. And I also kind of for the ease of identification, I have outlined the feature which later on got erupted. So there were a lot of activities, if you can see here in the beginning, and the activities before the eruption is what makes the evolutionary phase. So in our belief, we know that the activities which include mass motions. So, here are some dark mass, that is low temperature material available, which we can observe in different wavelengths as mass motions, and also some small intensity enhancements also, which we see in these images, as well as this intensity profile of X-ray emission. So these two kind of things are the primary ingredient of evolutionary phase. And the reason for investigating the activities in this phase is to find out whether they can help us realize what has given rise to what has triggered this particular feature, which later on we observe all the way from sun to the earth. So based on this short preview, I would like to outline the presentation which I am going to share with you. First, I will introduce the terms as I promised, and then I will move on to two of my recent researches which explore these kind of activities in the evolutionary, that is the pre-eruptive phase of flare, and they help us determine the magnetic field configuration. In one of the paper, we determined the magnetic field configuration before eruption, which was a multi-flux rope system. It is very difficult from the direct magnetic field observations to obtain this kind of magnetic field configuration is very difficult. So by mass motions and the flares we observe, we try to infer these kind of systems. And in another work, which I will be presenting later on, we have determined the magnetic field configuration of solar filaments. So directly moving on to the introductions. First of all, the activities occurring on our sun, since they are the central engine of space weather, as shown in the animated picture here in the right side, where there are a lot of activities going on the sun, mainly guided by the magnetic field evolution on the sun. And these activities, they expel radiation as well as particles, and these radiation and particles in combined form the space weather, even drive the space weather. So we need to investigate the activities which are occurring on the sun, primarily because it provides us the laboratory of complex plasma processes which are occurring in more than 1 million Kelvin temperature environment. And as I told, since these are the initial drivers of space weather, in order to have a better prediction of the space weather, we need to investigate the activities which are occurring on the sun. So let's move on to another term which I will be using is the solar eruptive processes. So the few examples which are kind of well known in the community are coronal mass ejections, solar flares, and solar wind. They are the primary contributors of the solar eruptive process which we know so far, and they are the drivers of the space weather. My research, starting from my PhD to my postdoctoral tenure, is mainly centered on the activities which cause solar flares and its aftermath. So in this presentation, I will give a more detailed discussion on the solar flares, but of course, the physical mechanisms which drive the energy release during solar flare, coronal mass ejection, and even solar wind is sharing the same platform, that is magnetic reconnection. So introducing a bit about solar flares. Solar flares are known as the transient short-lived brightenings, which occur, which are observed for a duration of 10 to 30 minutes most of the time. Sometimes they even are for the longer duration. And typically energy released from a flare varies in the range of 10 raised to the power of 28 to 10 raised to the power of 32 ergs. On the other hand, for small intensity class flares, the lowest energy observed energy release is obtained as low as 10 raised to the power of 25, or theorized nanoflares are 10 raised to the power of 24 ergs. As I pointed out, solar flares can be observed in across the entire electromagnetic spectrum. So multi-wavelength investigation is very important if we want to determine the physical activities and coupling of the mechanism which are going on at different layers of the solar atmosphere. And since solar flares are one of the most initial signature of eruption and probably the driver of eruptions in the inner heliosphere, we need to understand the flare mechanisms in order to refine our prediction of space weather and its impact on Earth and other solar system objects. So with this general introduction, let me move a bit more in detail to the flare energy release process. So based on different multivalent observation and their interpretation, the best model which can interpret all of these multivalent observation is put forth, also known as the standard model of energy release in the flare physics. So in the right hand panel, I am showing the cartoon of the standard model of solar flare energy release, which starts in this cartoon. I am going to explain a few features. So here we this half circular feature, semicircular feature is the coronal loop, and due to its twist, we have a process which is known as magnetic reconnection, which can take place at any part of the loop, but mostly it takes place at the apex of the loop. And since these coronal loops are magnetic field lines which have some free energy, that is non-potential energy available in it, due to magnetic reconnection, this free energy is provided to the ambient charged particles, and these charged particles, they get energized, and guided by the magnetic field lines, they come down to the lower and denser layers of the solar atmosphere, that is solar chromosphere. So as soon as the magnetic reconnection occurs, within a fraction of seconds, the charged particle from this region, they come down to the chromosphere and can be observed in higher energy X-rays, also known as hard X-rays. And later on, as soon as the energy is dumped in a very small portion, which is shown here by crossbars, the chromospheric evaporation or the chromospheric ablation occurs. Due to this process, the energy is again starting to get released in the higher layers of this coronal loop, and that's how we see the full coronal loop in soft X-ray. And when the plasma in these filled loops is cooled down, we see these observations of solar flare in extreme ultraviolet observations. So from this process, which starts with magnetic reconnection, then hard X-ray emission, and then the soft X-ray emission in the entire loop, it is clear that the solar flares can be observed across the entire electromagnetic spectrum. Because in the solar chromosphere, this can be observed in optical as well. And okay, so I have explained only up to the solar flare configuration of it, but this helical field line structure, what you are seeing, is actually the central engine of the eruption which occurs from the sun, also known as coronal mass ejection. So as soon as the magnetic reconnection occurs, this helical field line, that is flux rope, erupts from it, taking away the magnetic field which is surrounded to it, and it moves forward to expels away from the sun, and sometimes it also reaches to Earth. And this is why investigating the mechanisms which give rise to energy release on the sun as well as its different forms is very important. Okay, so moving back to the solar flares now. In the evolutionary stages, there are a lot of activities occurring on which are important to us, because based on those activities only, we will be able to trace the magnetic field structure as well as the plasma state, that is the thermal state or non-thermal state of the plasma, that is the energy content in the plasma. So the activities in early stage include X-ray precursors, plasma heating. So during the earlier stage itself, plasma heating can be up to as high as a few tens of million Kelvin, which I will be demonstrating later on. Then then a very important consequence of evolutionary stage activity is the activation and rise of filament. So I will introduce the filament a bit later, but this is the dark structure on the sun, and before erupting, it has a slow rise, which is very important in order to determine how the magnetic field wrapped around the filament is evolving. And finally, there are plasma flows, as probably you have noticed in the movie I have just shown. So these hot plasma flows are also very important in order to answer a few long-standing problems related to the formation of flux ropes. Mainly in the evolutionary stage, there are small intensity class flares. Small flares, if we plot the occurrence frequency of flare with the peak flux, we find that it follows a power law, which means that small intensity class flares are more frequent compared to the large intensity class flares. And that is what we see, that in the evolutionary stage, there are a lot of small intensity excursions. So it is very important because while for the case of coronal heating, if they are these small intensity class flares, that is either micro flare or even lower intensity class flares are termed as nano flares, they are theorized to be for the large scale heating of the solar corona. The other theory is wave heating, but one of the theories for the coronal heating. So coronal heating problem is, while the temperature of the surface of sun is lower in a few thousand Kelvin, the solar corona is a few million Kelvins. So this coronal paradox, one of the way by which the large scale coronal heating is explained is nanoflares. So this is one of the consequences of investigating the evolutionary stage. The other thing is, we can also answer a few open questions, like how flare properties change over a wide range of magnitude, that is from X class flares to M, C, or even B class flares, and are these similar? And of course, as I told, the advantage, the virtue of investigating the flares in the evolutionary stages, we can trace pre-eruptive magnetic structures, and these small flares most of the time do not disrupt them. Once the structure is disrupted, we need to follow them in the heliosphere in order to investigate their physical mechanism. But if they are attached to the sun, these kind of small intensity class activities can actually help us trace their magnetic structure, as I will be demonstrating in the coming study. So this is the investigation I have, I along with the colleagues in USTC have done back in 2018. In this investigation, we have analyzed a flare precursor, and through this we obtained magnetic field configuration of a multi-branch flux rope system. So let me first introduce the event. So this 22 June 2015 event. So this actually, the main event was M6.9 flare, which was actually associated with eruption, as you can see in the left panel's movie, which is obtained in 193 angstrom UV channel. And as you can see, at around 18 UT, there is eruption which leaves the surface of the sun. But before this activity, there are a lot of C and sometimes even B9 class activity going on, which continuously helping in rising the X-ray background up to C class level before the eruption occurs at M class. So it was very important evolutionary phase which finally led to an eruption, and that is why it was one of the this was the focus of our study. So in X-rays, in M6.9 flare, there were two precursors, as we can see here, and these were investigated in another paper by Wong et al. But before these two precursors, there are a lot of different activities. For example, this including B9 and C1.1 flare. So if we consider this as a full flare, this is some precursor we see. So this particular time range is the main focus of our investigation, as can be seen here. So if we zoom in a bit further to this particular X-ray intensity profile, we see that the excursion here before this C1.1 flare is quite small. But please believe me, this particular excursion is going to tell a lot of important things about the pre-eruptive structure. So what we then next did is we obtained the images in AIA 131 angstrom channel. The 131 angstrom extreme ultraviolet channel actually shows the high temperature, that is more than 10 million K plasma on the sun. So when we have obtained the images at this point where we saw this small excursion before this C1.1 flare, this is shown in panel here. In the central panel, we are showing the images taken in the rise phase of this C1.1 flare, and in the maximum phase, in the gradual phase, we have the image shown here. In order to determine, in the precursor phase, what we see here is that the brightening is kind of threaded here. If you can see, two threads are clearly visible, and these two threads actually corresponds to the polarity inversion line. How we can know that? For this purpose, we have overplotted the magnetic field contours. So the white region corresponds to the positive magnetic field, and the black contours correspond to the negative magnetic field. So the neutral line between them is actually where the precursor emission, the threaded precursor emission, is observed. As the flare moves on to the rise phase and then to the gradual phase, we see more typical kind of coronal loops associated actually with the same active region and same brightness we see during the precursor phase. And later on during the gradual phase, we have a thick plasma filled loop. So by investigating the UV images, we kind of ascertained first thing that the precursor enhancement in X-ray emission is actually coming from the same location as the main flare. Now moving further, in order to determine the plasma characteristics, since from AIA instrument onboard solar dynamic observatory, we have 6 channels of extreme ultraviolet observation images. We use them in order to determine the emission measure maps in different temperature bands. So here I am showing the emission measure maps in 5 to 10 kV, 10 mk and 10 to 20 mk. In the middle and bottom panel corresponds to the time for which the AIA 131 angstrom images are shown in the top panel. So from this emission measure maps, it is very clear that during the precursor phase itself, the enhancement in the temperature has reached up to 20 million K. When we plotted the X-ray contours in high energy, that is 12 to 25 keV, this kind of observed as a co-spatial to what we have observed in the precursor phase enhancement in the AIA 131 angstrom. So this confirms that the small excursion before C1.1 flare actually produced the plasma of more than 10 million K, and the location of the enhancement was along the polarity inversion line. In order to further investigate the process which gave rise to this precursor emission, we then moved on to the deriving the coronal field lines. And for this purpose, we use the vector magnetic field observations obtained from heliospheric magnetic imager on board Solar Dynamic Observatory. And using the nonlinear force-free field extrapolation technique, we have determined the magnetic field structure. And in what I'm showing in the right panel is the magnetic field structure of the field lines which are twisted. So there, when we determine the coronal field lines from the whole magnetic field region, we have the twisted as well as the non-twisted field lines. Twisted field lines are important to us because these are the lines which have the magnetic energy, free magnetic energy available with them, and that can be used later on for flares. So when we try to indicate the twisted field lines, we found that this actually shows a flux rope kind of configuration, but with separate branches. For example, the lowest branch we can see here is below 5 megameter, and the highest branch is, so these are the potential field lines, but before this there are 5 branches, and the 5th branch is as high as up to 25 megameter. So by investigating the coronal magnetic field structure using the extrapolation, we found that there existed a multi-flux rope configuration. So this is the different perspective of the flux rope as we see here. And we also have the opportunity of deriving the sign of twist. So the black lines showing here are actually corresponding to the region of positive twist, and the blue overlying lines here are actually the field lines during the gradual phase of the flare corresponding to the sheared arcade. So by this means we have although obtained the coronal magnetic field lines, but it is definitely important to overplot these onto observations in order to confirm, because this is just numerical model after the initial magnetic field configuration we obtained from the observation. So that's what we did. Oh, okay, but before this, from the extrapolation point of view, if we, so here is the magnetic field configuration extrapolation from vector magnetic field observations we have for this active region. And if we plot the twist map, as I told you that this is possible to obtain the twist for each and individual pixel from the observation. And if we plot the twist map, we can see that the flux rope actually aligns with the polarity inversion line. And this, if we recall the observation of emission during the precursor phase, this also aligns with the in the enhancement during the precursor phase. That I will also show later. But in addition to this twist map, if we also have the twist plus a squashing factor. So squashing factor also tells about how close the magnetic field lines are in a certain region. So this is actually the XY map, and this is the X-shade map, and cut along this line. So when we have the X-shade map of the twist plus squashing factor plotted, we can see that there are different branches of the flux rope clearly seen. So 5 branches of flux ropes are there. And in addition, there are regions of positive twist which existed before the flare, but after the flare, when we plotted the same map for the observation after the flare, we found that the twist has been reduced. This is a signature of magnetic reconnection. So what happens is that due to magnetic reconnection, the twist of the field lines which are involved in the reconnection process gets reduced. So these are the 2 points. So we have reconnection in different branches of the flux rope, as we can see here. So this is the first and second branch, and we have reconnection here. And this is another branch where we have the reconnection. And now if we overplot the extrapolated magnetic field lines onto observation, what we see that the precursor enhancement very clearly matches with the foot points of these field lines. This is remarkable in the sense that the numerical extrapolations and the observation agree with the fact that the activity occurred in within the magnetic flux rope system. And that is the region that we have enhancement in 131 angstrom or even in 304 angstrom, which is close to chromospheric height. Then we have the calcium observation from Japanese mission SOT, and also from IRIS mission, which observes the transition region between the chromosphere and the corona. We can see the foot point emission all over the solar atmosphere, which corresponds to the foot point of the flux rope which we obtained from the numerical analysis. In the bottom panel, I'm showing the same maps without the foot point overlapping in the precursor time, and we can clearly see that the precursor enhancement also shows some bright region which corresponds to the foot point of the flux rope. So these bright kernels are actually also the signature of magnetic reconnection which occurred within different branches of the flux rope system. Another signature of the reconnection is the restructuring of magnetic field. This is very important because with the high resolution observations we have in hand, if we closely look for the observation at 1632 UT, that is during the precursor phase, if we compare the first panel with the ongoing panels, for example, this panel here, we see that there is some restructuring between this threaded line occurred. Restructuring is also a signature of reconnection, and this tells that braided magnetic field lines have undergone some restructuring. And according to Parker 1983, the braiding may dissipate currents and which is induced by the entangled field lines, and this dissipated current actually can help trigger the whole system. So with the observations, I have demonstrated that during the precursor phase, during the precursor enhancement, we have multi-flux rope system and there is some restructuring going on. In addition, we have other signatures of reconnection, and that includes plasmoids. So we have the plasmoid observation, as can be seen clearly here. And when we kind of obtained the thermal characteristics of this small plasmoid blob here, we found that this plasmoid initially has a temperature of 10 million K, which later on reduced after a few minutes up to 7 or 8 million K. And this high temperature actually plasma can only be able to be generated from the reconnection process, which occurs somewhere here, somewhere beneath this field line, which has the plasmoids in it. So we have around 4 arcsecond wide discrete episodes of plasmoid, as we can see, and the temperature was around 10 million K as maximum. And when we obtained the thermal energy of these plasmoids, we found that they are ranging between 4 to 9 into 10 to 27 ergs. So this actually amounts to a microflare. So during the precursor phase, we actually clearly observed microflares which are associated with the reconnection going on in different branches of multi-flux rope system. This is the bidirectional flow which we obtained from the same plasmoids, as can be seen from this time distance image. So here, when we obtain the time distance image along the slit shown here, we see that the plasmoids are moving in both of the directions. That means the reconnection took place somewhere at this point in the center, and then the plasmoids had moved in the both direction. This is also a very clear signature of reconnection. And finally, about the plasma state. So in order to determine the plasma state, we have analyzed the X-ray emission obtained from this region. So X-ray emission from RESI emission has been analyzed, particularly the X-ray spectra in 6 to 20 keV. So during the precursor phase, if we see, so this is the time when precursor enhancement was there. And during the precursor phase itself, if we fit the observed X-ray spectra with the isothermal and non-thermal functions, what we obtained is that the temperature of the plasma was around 20 million K, which kind of agrees with what we have obtained from UV observations. And also one of the important thing which we can obtain from the X-ray spectral fit is the non-thermal electron index, and this was 6.3. Usually during the main phase itself, the non-thermal electron index for very high flares also can go as low as only up to 4. And this index actually tells how flat the X-ray spectra is. And with this, we can also interpret how high the electron energy was, which gave rise to this spectra. So during the precursor phase itself, it is clear that the electron energy which gave rise to the precursor emission was very high. On the other hand, during the main phase, we have a typical 17 to 20 million K temperature as we obtained from the X-ray spectral fit. And in addition, we also have the non-thermal spectral index in the range of 6 to 8 in negative actually. So from this X-ray spectral analysis, as well as the UV and nonlinear force-free field modeling, the conclusion we have to offer is as following. We have determined the kinematic and thermodynamical characteristics of the reconnection within a multi-flux rope system. And as I told you, there are several signatures of magnetic reconnection which are definite. For example, we have non-thermal electrons up to 20 keV as observed from X-ray spectra. There is availability of hot plasma in the precursor region up to 20 million K. And the plasmoids which generated during the reconnection shown a bidirectional outflows. So these are the signatures of reconnection. So with this, we kind of established that during the precursor phase itself, we have internal reconnection within the multi-flux rope configuration. And that resulted in complex ejecta later on, which we observed in the interplanetary space. So, and also from this observation, we have that the internal reconnection seemed to favor plasma relaxation, thus providing a mechanism for small intensity class flare or compact flares. And very important conclusion which we can derive from the list of observational as well as the modeled results we have is that following the eruption, there was an internal reconnection which may continue when the CME is moving forward in the interplanetary space. And this internal reconnection actually may contribute to the heating of the CME, which is observed in the outer corona as well. So from this investigation, by probing the multi-wavelength emission during the precursor phase, we have obtained very crucial information of pre-eruptive magnetic field configuration and the processes going on, which can help trigger the whole system. So this is one of the investigations. And I would like to now move on to the second half of my presentation, which is where based on the activities of the mass motion in a solar filament, we'll try to derive the magnetic field configuration of the filaments. So here I am showing introductory picture where there are a lot of black striped lines are available. These are actually known as the filaments, solar filaments. If they are observed on the limb side, they appear as bright and also known as prominences, but the filament and prominences are actually the same features observed against the disk in dark and against the limb in bright. So the important things which we would like to investigate about the filament is that since these are dark feature all over the disk and they hang in the corona. So one of the things which comes in the mind that how these mass material can hung up in high in the corona against the gravity of the sun. So for this purpose, it is important to know the magnetic field configuration of the filaments. So based on the observation and numerical point of view, there are two magnetic field configuration which have been proposed so far. One is the shared arcade, and the other is the flux rope. So the helical field lines are the flux rope configuration. In both of these configurations, the filament material is known to accepted to lie in the depths of the field lines. So that is how the filament material hangs up in the corona in the depths of these field lines. So in the bottom panel, I'm showing the complex 2D to 3D structure of how the field line actually appear in the numerical simulation, as well as sometimes in the backed up by observation as well. So in the bottom panel, this is from Alonier et al. 2012 2002, and then we have from Bobra et al. Where the flux rope is kind of shown, which contains the filament material, which basically follows what we observed from the H alpha observations. So observing the filament is very important in order to know the magnetic field configuration, but observations also created some kind of more complexity in the configuration. For example, there are observations by Go et al. And Liu et al., who later on found that there is a complex configuration of filament with a hybrid structure. For example, in some cases, the flux rope and shared arcade system are found to be in a same filament system, although separate apart in Go et al., for example. And however, in Liu et al., they observed multiple branches of filament, as can be seen from this observation. And based on these observations, they have proposed a double-decker structure of a filament magnetic field configuration. This double-decker can contain two flux ropes, one on top of each other, and in other configuration, the flux rope on top of a shared arcade. So in fact, there are three magnetic field configurations of a filament now known so far. So based on a high resolution observation I obtained from new vacuum solar telescope installed in Yunnan Astronomical Observatory, we will try to trace the magnetic field configuration of the host magnetic field configuration of this filament. So for the purpose, actually, there was a small B class flare before our observing duration. So in the panel here, I'm showing the X-ray intensity profile. And just after this flare, we have observations from this NVST for around 3 hours. So right after the activity, which is also seen in H alpha in the form of bright kernel here, we have in the observations, we can clearly see that there is some kind of oscillation along the spine of the filament structure we can see here. So I'm running the movie for a few cycles. So this is a movie of 2 hours, which is obtained from the which is prepared from the observations available from NVST. So from this movie, it is the observational facts are the V class flare which occurred in the vicinity and initiated some disturbance in the material we observed from NVST. So this was westward direct disturbance that originated in the filament. At one point of time, the filament material moves as far as around 20 arcsecond away from the spine. For example, if we see at one instance, for example, here, so if we understand this as a spine, the material has moved as far as around 20 arcsecond. So although it is clear that this oscillation is along the spine, but there is some transverse movement is also very clear, as can be seen here. And additionally, as I will also demonstrate later, there was some also rotation in the material, which we can see here. So in order to quantify the oscillations which we have obtained, which we have seen in the observation I have shown in the form of movie, we took help of the AIA 171 angstrom maps. In AIA 171 angstrom actually observes the around 2 million K plasma on the sun, and that is how we can clearly see the filament and also the surge from this this wavelength channel. So using the sequence of images in this observed in this channel for around 5 hours, when we have made the time distance maps along the slits shown here. For example, for one slit S1, I am showing the time distance map here, and it is very clear that after a surge, which is seen as bright here, we have the oscillation in the dark material, the filamentary material, and the oscillation is in the also in the third cycle is also showing some dampening. Since the slits are almost inclined close to the spine of the filament, we can understand these kind of oscillations, call these kind of oscillations as longitudinal oscillations. But in addition, since the amplitude of such oscillations is very large, the classification for such longitudinal oscillation is large amplitude longitudinal oscillations. So it is very important to investigate the such kind of oscillations, because we can actually probe the magnetic field strength and different characteristics of magnetic field through these oscillations, as I will demonstrate in next slide. So when we have the oscillatory pattern in hand, we fitted it using the damped sinusoidal function as shown here. So using this damped sinusoidal fitting, we obtained the period of such kind of oscillation in addition to the damping factor. So here I am plotting the period of the oscillations which we have obtained from such a fitting for the positions along the spine. And as we can see that this period is around 1.4 hours. And using a simple pendulum analogy that with the restoring force as gravity, we can actually relate the period of this oscillation with the radius of curvature of the field lines on which this magnetic filament material is rolling back and forth. So using this simple analogy, when we have the period in hand, we also estimated the radius of curvature. And the radius of curvature is found to be varying in the range of 150 to 250 megameter, which are actually large in compared to a normal magnetic field, bipolar magnetic field. And that's where they indicate that the magnetic field which hosts such a large amplitude longitudinal oscillation is actually shared arcade. In addition, so from a longitudinal oscillation, we found that the magnetic field, we inferred that the magnetic field could be shared arcade. But we also have the observation in the blue wing and red wing of H alpha from the NVST in plus minus 0.3 angstrom. And using this simple asymmetry analysis, we have determined the Doppler maps. So the Doppler maps are actually the maps which shows the direction of material movement along the line of sight. So here I am showing an average Doppler map where the red material, red pixels indicating the material moving away from us, while the blue pixels showing the material coming towards the line of sight, that is us. So from this average Doppler map, it is clear that there was a sequence of mass motion where the material close to the spine in the lower side is going up, while the material on above the spine on the northern part of the spine is going away from us, that is down. So this sequence of motion can only be explained if there is a rotational motion close to the spine. And this is very clear along the whole spine, not just one part of it, but along the whole spine. And this is similar to what we have observed, similar to the location what we have observed the longitudinal oscillations as well. So from longitudinal oscillations, we found that the shared arcade could be one magnetic field configuration, but that actually cannot explain the rotation what we obtained from the Doppler maps. So in order to corroborate these clearly identifiable mass motions after a flare, we infer a double decker magnetic field configuration where the bottom structure is the shared arcade which hosts the longitudinal oscillations, while on top of it is a flux rope which actually hosts the rotation which we see in the Doppler maps. So from the mass motion itself, we have which is generated due to a small flares, we have inferred the magnetic field configuration of this filament, which is not possible using the direct magnetic field estimations. So here is a summary from the investigation we have from this particular set of observations. From the high resolution H alpha observation, we have two kind of motions which are simultaneously. One is large amplitude longitudinal oscillations, and the other is rotation around the spine. So the longitudinal oscillations are indicative of shared arcade because the radii of curvature which we obtained from fitting the oscillations is quite large. However, in addition, we have rotational motion also, which is confirmed from the Doppler maps, and this is around the spine is typical to the flux rope configuration. So based on these hybrid mass motions, we have obtained the hybrid structure of the magnetic field configuration. So this is my final slide. So I have been investigating the cases of evolutionary phase of flares where we have found that inferring the pre-eruptive magnetic field structure using the evolutionary activities is kind of very important, very crucial. And in addition, we can also have the information on energetic state of the plasma as well as their potential as the triggers. So using this information, and also since the new age instruments, for example, DKIST, Parker Solar Probe, and Solar Orbiter are specifically targeting the small flares in the context of coronal heating, a systematic study of these events is required, supported by numerical simulations, and that can be very relevant for the future direction of space weather prediction. So this is all from my side. Thank you very much. I would like to have some questions if you have.
Thank you, Arun. Thanks a lot for really nice talk on solar eruptions. So now we can take a few questions. Yes, Patricia, please, can you ask your question?
Yeah, thanks very much. That was absolutely fascinating. I know it's not the main focus of your studies, but do we understand enough about these things now to be able to predict what the long-term likelihood is of flares and well, space weather generally? Is it likely to get stronger or weaker or stay more or less as it is?
Actually, so you are talking about the solar cycle or the prediction or the prediction of space weather?
I'm talking about the long-term solar cycle. I mean, I know obviously about the solar cycle, but you know, what's going to happen in 500 years, 5,000, 5 million years?
Actually, I think that the dynamo process, which mostly governs the solar cycle, is more or less known in terms of observation as well as numerical simulations. But for the longer and very long term cycles, I think we still need a lot of data in order to get to such information.
Okay.
Yeah, actually, I can give you an example of it because I was involved in a paper where the prediction of cycle 25 was taken up using the AA index and the spotless days. So during this investigation, actually, we found that there are three kind of literatures which are available on the prediction. One is that the activity will be weaker in cycle 25. The other kind of literature predicts that the activity will be stronger, and the third kind of literature is that. So what I mean to say is it is really difficult from the observational and numerical simulation point of view about just the next cycle. So I think this is this is far this is still a time for us to reach to a level where we can have a long-term prediction.
Okay, thanks very much. Anyway, it's fascinating to see just how much you can get out of the observations you have got. Thank you.
Thank you very much. Thank
you. Now, can we have any more questions? Because we have, the time is almost up, so we can have 4 or 5 more minutes because we had started after 5 minutes. So we can have 1 or 2 more questions if there is any. Okay. No? Okay, then I can ask one question, Arun. I'm curious about how you differentiate the structures of long scale and small scale magnetic fields, and also how the interaction of those magnetic fields are different.
Okay, so for example, I think your question directs me to this slide, right?
So actually, it's more like a general, like the magnetic fields which are governing for the very long. I mean, it's the magnetic fields which are even going up to the corona, what you call corona of the sun, right? And
yeah. Okay, so I think this the introductory slide is going to be more relevant to show in this.
Yes.
Okay, so actually what I understand from different scale of magnetic structures is that the small scale magnetic structures help building the energy, which either energy or leading the large scale structures towards eruption. These are large scale structures which later on erupt and affect the space weather. But I think the connection between the large scale structure and small scale structure is the flux feeding. So these small activities actually feed the flux, and this help large scale structures to later on erupt and give rise to the CME, which we observe coming all the way from sun to the earth.
Okay.
And if it is the long term, if we are talking about dynamo, for instance, where there is a 11-year cycle and then there are a lot of long period cycles are going on. So I think this is more I think in comparison to the dynamo activities, these all structures are, I think, small scale.
Okay. Thank you.
Yeah.
So now I think we don't have any more questions. So Arun, thanks a lot for this very nice session. So